Let's do a thought experiment. I'll put my cat in a steel chamber along with a radioactive device. That's probably a bad idea. My cat has a 50% chance of either dying or surviving. Unless I check the box, I can't really know its state. Now, if the cat is a quantum object, it is both dead and alive. If it's just a regular cat, it is either dead or alive. The quantum cat is in a superposition of states. But if you look inside the box, you destroy the quantum state and the cat becomes either dead or alive. That's a simple idea, so keep that in mind as we try to understand the dual nature of quantum objects. Let's do the double slit experiment. We're going to shoot electrons through a screen with two slits in it. If there's a back screen placed behind, what would you expect to see on the screen? Since electrons are particles, there should be two concentrated areas of electrons. Quite like if we made sand pass through the slits. But this is not what we observe. What we see on the back screen is an interference pattern, which is something that is created if you were to pass waves through the slits rather than particles. Like if we did with light waves. The waves interfere with each other to produce areas of high intensity and areas of nothingness. So, is this experiment implying that electrons, which we know to be particles, have wave properties? Maybe observing the electron can help us solve this mystery. But things get even stranger at this point. When observed, they no longer show wave-like properties and we get two concentrated areas of electrons like we would with particles. Remember how I said our cat is both dead and alive before we check and see its state? And that our observing is what makes it one or the other? The same concept is applied here. The electron is both wave and particle, and it is only when we observe that it becomes one or the other. Now that we understand wave-particle duality, we can move on to the uncertainty principle. First, let's discuss wave and particle properties, since our quantum object is both. A wave is not restricted in one position. A ripple, for example, is all over the pond, but the wave can have a defined wavelength. And if you look at this equation here, it basically says that the momentum times the wavelength is this constant called h. We can't go in depth of what this is, but we can use this equation to find the momentum. Also keep in mind that if momentum increases, wavelength decreases, and vice versa. So if I know the wavelength, which I do for a wave, I can find out its momentum. While on the other hand, there's a particle, which has a definite position. However, it has an unmeasurable wavelength, therefore we can't find its momentum. Now let's look at our quantum object. It can have a variety of different positions and momentums. But there are going to be some places where our particle is most likely to be, and some momentums that it most likely has. Can we determine these areas without measurement? Because remember, measuring means we gave it a definite position and momentum. Just like measuring meant the cat became either dead or alive. We'll try to find the position first. We'll add different possible wavelengths the quantum object could have and get a localized wave. There will be places where the object is most likely to be and places where it's least likely to be. And the more waves you add, the more certain you become of its position. But we did something in this process. We kept adding waves over waves, but that means we no longer have an accurate wavelength. And an uncertainty in wavelength means an uncertainty in momentum. The same thing applies the other way around. By decreasing the uncertainty in momentum, you increase the uncertainty in position. And all of that information can be described in this equation. So there you have it. We've discussed superposition, the idea that things can mean a multitude of states so long as you don't measure them. We did the double slit experiment, which portrayed electrons as both waves and particles. And finally, we applied our knowledge to grasp the uncertainty principle.